Humans process language intuitively, reading words as a continuous flow of meaning. But underneath every modern artificial intelligence is a rigid mathematical environment. Neural networks cannot read discrete text strings. They only process dense numerical arrays. To understand modern architectures, from BERT to GPT-4, you must examine the foundational input pipeline bridging this gap, the mechanism transforming raw text into math. Early models handled this with simple word-to-vector mappings. As the industry scaled up to massive generative models handling multilingual data, that structure had to evolve to process effectively infinite vocabularies. Without a precise mathematical transformation at the beginning of the pipeline, the attention mechanisms and sequence generation in modern AI literally cannot function. The modern input pipeline is divided into a strict two-step process, separated by a hard functional boundary. This diagram illustrates the pipeline's two distinct functional areas, tokenization and the embedding layer. Phase 1 outputs discrete integer IDs, stripping away raw text. Phase 2 converts those indices into continuous, high-dimensional vectors. This creates a strict architectural distinction. Tokenization dictates exactly what data is represented. The embedding layer dictates how that data is represented. Tokenization is purely structural. It assigns zero semantic meaning. The embedding layer operates as the exclusive semantic engine, establishing a separation of duties that keeps the model efficient. Before a machine can interpret language, the text must undergo discretization. This is the mandatory act of breaking continuous human language into finite, countable units that can be indexed. This chart outlines the first, most intuitive approach, word-level discretization, breaking sentences down strictly word by word. This method served early models well. It is highly interpretable for humans, and a complete word naturally carries a high level of semantic meaning, but it carries a critical mathematical flaw. A word-level dictionary requires a unique entry and a corresponding vector for every possible word across every language and specialized domain. This creates the out-of-vocabulary problem. Rare terms and misspellings, or newly invented words, cannot be mapped by the model because they lack a dictionary index. Expanding the vocabulary to millions of words to catch every variation is a computational impossibility. The resulting embedding matrix would consume too much memory to run on any GPU. Using word-level units forces engineers into an impossible trade-off: either suffer massive inefficiencies through extreme matrix bloat, or discard vital rare words and lose the information entirely. To bypass the out-of-vocabulary problem, you could swing to the opposite extreme, character-level discretization. Breaking text into individual letters ensures a tiny vocabulary size. However, as shown here, spreading a single concept across 8 separate letter tokens destroys immediate semantic meaning, forcing the model to work much harder to understand simple concepts. The industry standard adopted by GPT-4 sits between these extremes. It uses subword tokenization algorithms. These iteratively merge frequent character pairs in a training corpus. Common words remain whole, while complex words fracture into logical pieces. These smaller, reusable components allow the model to reuse mathematical representations across related forms. The token learn can be reused whether the word is learning, learned, or learner. Subwords hit the required architectural balance. They keep vocabulary size strictly constrained, typically under 200,000 tokens, completely eliminating the out-of-vocabulary problem. With the subword dictionary established, the tokenizer's mechanical output pipeline is straightforward. It normalizes text casing and whitespace, then maps the resulting subwords to unique integer IDs. Looking at this table, we can trace a human sentence directly into the machine. The tokens I, am, and learn are instantly converted into the indices 0, 1, and 2. At this exact moment in the pipeline, the text ceases to exist as language. It is now solely an array of arbitrary numbers. It is crucial to avoid the token illusion. These integers contain absolutely no relational data, no semantic proximity, and no structural understanding. Token 0 and token 1 are not mathematically related just because their numbers are sequential. The tokenizer acts purely as a rigid pre-programmed dictionary. Its only job is to format the data so the true semantic engine can read it. That semantic engine is the embedding matrix. This is the mechanism that actually assigns meaning. The dimensions of this matrix are precise. The number of rows equals the model's total vocabulary size, and the number of columns equals the embedding dimension. In mathematical theory, mapping a token index is equivalent to taking a massive one-hot vector and multiplying it by this entire embedding matrix. In practical computation, matrix multiplication is too expensive. As this diagram illustrates, modern frameworks perform a direct row lookup. Index 0 simply points to row 0. The output of this lookup is a dense vector of continuous numbers. Depending on the model, this vector might contain 512, 1024, or 2048 dimensions. Larger dimensions encode exponentially greater semantic nuance into every token, but they dramatically increase the memory overhead required on the GPU. The specific numbers inside these vectors are not hard-coded by engineers. They are continuous weights, updated and learned across billions of iterations during the model's training phase. This simple lookup operation places an isolated, meaningless token into a continuous mathematical space where semantic relationships can finally be calculated. We can ground this theoretical pipeline by looking at a practical engineering application, an English to Hindi sequence-to-sequence translation model. Specifically, we evaluate the pre-trained Helsinki NLP Opus MT architecture. This terminal window displays the exact tensor shape of the model's embedding layer, isolating its vocabulary and dimension boundaries. Translating this tensor output back into architectural reality means an exact vocabulary of 61,950 tokens is mapped into a 512-dimensional continuous space. This architecture utilizes shared embeddings. Both the English input hitting the encoder and the Hindi output generated by the decoder exist within the exact same vector geometry. Instead of memorizing a rigid dictionary, the model calculates semantic proximity and structural agreement within this single shared 512-dimensional construct. This workflow shows the complete journey for a specific input sentence, "I am studying embeddings," as it is translated into Hindi. In Phase 1, the text hits the tokenizer, breaking down complex words like embeddings into subword indices. In Phase 2, those discrete indices hit the lookup matrix, pulling the corresponding 512-dimensional dense vectors. These vectors position the concepts relative to each other. This geometry allows the model to capture syntax, gender agreement, and technical vocabulary entirely through spatial proximity. Tokenization created the structural units, but the embedding layer provided the environment for comprehension. Converting discrete strings into continuous vectors provides the mandatory mathematical foundation for attention mechanisms, multilingual generation, and the entirety of modern AI logic.